Good morning, good afternoon, or good evening. This is your IT Explained, and in this video we're going to be delving into the troubleshoot loop prevention mechanisms. Specifically for this one, we're going to go into filtering and touch a little bit on tagging. So this comes out of the official Cisco examination topics 1.3, which is troubleshoot loop prevention mechanisms, filtering, tagging, split horizon, and route poisoning. Now it's important to note what's actually on the screen. It says troubleshoot loop prevention mechanisms. So it's not necessarily about implementing loop prevention mechanisms or make sure that you can prevent loops. You may be thrown questions that have, here's a configuration where we have actively prevented loops in the environment, but now we're not receiving any traffic destined to this network, or we're not receiving route advertisements from this network after we've implemented these loop prevention mechanisms. So you just got to be prepared that if when you're in the exam, it's not really going to necessarily ask you, hey, prevent loops by implementing tagging here, or what is wrong with this route map when it comes to preventing a loop. It may just refer to, hey, we've prevented loops, but now this other thing isn't working. What is the best fix? Okay, so with that in mind, we're just going to go through the actual technologies that they've mentioned and explain how they work. And that way, when you understand the basics, you'll then be able to fix incorrect configurations, or if they've configured things that are just not achieving their desired outcome, you should be able to identify why and then provide the correct answer in the examination going forward. Okay, so that's enough ramble. Let's just start with the real basics here. So what happens in a routing loop? Round and round we go till TTL reaches 0. Now, hopefully you're aware what TTL is, but a quick overview is every packet that's sent at a layer 3 level is assigned a time to live value. Now the default that's applied is 255, and every time a packet goes through a hop, it is reduced by 1. So a router will receive a packet, let's say it has a time to live of 250 as it receives it. It will decrement it to 249 as it sends it out. Now if a router receives a packet that has a TTL of 1, it will reduce it to 0, and then that packet is dropped, and all packets that come in with that TTL are then going to be dropped once it reaches 0. And that's the inbuilt layer 3 security to prevent loops going on forever. All right, so loops don't go on forever as long as they're abiding by this. They will just drop traffic eventually, but it's still an issue because it takes up bandwidth, and ultimately we're not getting the traffic to the destination that we wanted it to get to. All right. So yeah, as I mentioned here, it can happen even when you've configured technologies correctly. Once you start to get into more complex environments with many different things, different technologies, different routing protocols, you can still run into them even when you've implemented things by the book. So this is where you're going to have to start thinking at a deeper level, at the CCNP level. And you're ultimately creating a denial of service if you have a routing loop, because the traffic is destined for somewhere that's meant to go, but the result is it just goes around and round and round, or back and forth and back and forth. So wherever that's meant to reach, wherever that traffic is meant to go, it's not going there, meaning that you've denied the service. So it's something you want to avoid if you can, and we're going to go through different ways that you can avoid routing loops. So starting off with filtering. Now it's quite an ambiguous or vague term, so we're looking at that examination topic that we're going into in this video. Troubleshoot loop prevention mechanisms filtering, that's all it says. So what is that referring to? Are we filtering using tags? Are we using actual filter lists? distribute lists, prefix lists, ACLs, and how they all interact. It's kind of vague, so I thought the best approach is to make sure that we cover off on pretty much everything I just mentioned there. Now thankfully it does mention tagging as the next thing after filtering, so we don't have to worry too much about filtering based on tags just with this keyword here, filtering. But we will go into filter lists, distribute lists, and prefix lists, and also how they use ACLs. So yeah, there are many ways that we can filter traffic, and basically all of them can be used in some way or another to help avoid loops, given any particular situation. Yeah, and we're just about to crack on straight away, and we'll go into distribution lists first. So if we look at that quote on the screen, we have the following description of a distribution list. Allows the filtering of network prefixes on a neighbor-by-neighbor basis using standard or extended ACLs. So remember the name here, because it's going to get confusing as we go into the other like prefix lists and filter lists. Distribution lists, they control how you distribute traffic, how it's actually distributed. So on the right hand side of the screen, we've just defined an ACL, and then underneath that, if you look at the router ERGRP 23 statement, inside of that protocol, we have distribute list ACL filter, which is the name of the ACL, in. And that's the basics of how you can use a distribute list. You just define distribute list, and then what you're actually matching against, and then the direction, if it's going into ERGRP or out of ERGRP. So if then we look up at the ACL filter, it's an IP access list, a standard access list called ACL filter, where we are denying that particular network, and then permit any after that because of the ACL's implicit deny at the end of an ACL. We have to override that with an explicit permit any. So what is happening here? If we look at the distribute list command in ERGRP, it's distributing based on ACL filter, so and into ERGRP. So coming into ERGRP, it's going to deny any routes or route advertisements for 192.168.0.0, but then it's going to allow everything else. That's the basics of it here. So perhaps in this example, that particular network is causing a route loop as it comes into the ERGRP process on router 3, and so we're just using a distribute list to deny it as it comes into ERGRP. Now moving on to a prefix list. Now prefix lists, they can easily be confused, but if we look at the definition, it starts the exact same as a distribution list. So allow the filtering of network prefixes on a neighbor-by-neighbor basis, that's the same so far, but using a prefix list. So it's like referring to itself, a little bit confusing, but the difference is in a prefix list, you're not referring to an ACL. A prefix list basically replaces an ACL. So a prefix list is a different option when it comes to the distribution of traffic. And as we see here, we're using the same command, distribute list, but now we're actually specifying a prefix list called myPrefix. So instead of using an ACL, you can use a prefix list, which is a list of network prefixes, right? So remember that in the name, it's not, so a prefix list on its own is not what you use for distributing traffic, controlling that. It's where you define the prefixes, the network statements, okay? And then you can use that with the distribute list in this example here in ERGRP anyway. So remembering what we did before, the only difference is if you want to specify a prefix list, you have to put in that keyword prefix. If we just wrote distribute list myPrefix in, what's going to happen is the device is going to look for an ACL called myPrefix and apply it. And if you don't have an ACL called myPrefix, but you do have a prefix list called myPrefix, like we actually have here in this example, what would happen is it's not going to say, hey, I found this prefix list called myPrefix, but you don't have an ACL called myPrefix. Is this what you actually wanted? It's not going to do that. It's not going to spit out an error. It's going to accept the command, even if there is no ACL called myPrefix. So you need to really be cognizant of this. Make sure that if you want to use a prefix, you remember that keyword. Okay, and then that's it. That's basically the same as the previous example. If I go back one slide on distribution list, it's basically the same, just that one extra keyword. But now, how is a prefix list different? Now, this is a little bit confusing, so just switch on for a second and really pay attention, because it can definitely be confusing when it comes to this last part of the command. So in this example, I've specified two sequences. Now, I didn't actually specify the sequence number in the first line. So if we look down to the show IP prefix list down the bottom, we can see it defaulted to sequence 5 when I didn't specify. So the default sequence when you don't specify is sequence 5 for a prefix list. So we've defined it with IP prefix list, the name, and then you do sequence 5, for example, and then permit or deny. And so we're permitting 172.20.0.0/16 less than or equal to 32. And then on the next line, doing the same thing, but on sequence 20, and then we're permitting 192.168.0.0/24. No less than or equal to statement or anything after that, just that exact network. All right, so what does this actually do? All right. Now, yeah, so this is confusing. Bear with me and just try to apply yourself, because this is important that you understand how this works. I can almost guarantee you'll get tested on this in your ENARSI exam, but I can't guarantee it. But almost guarantee, so definitely pay attention. So what is happening is it's permitting 172.20.0.0/16 where the network statement that it's receiving is less than or equal to 32 bits in length. So where the prefix is 32 bits or less than that, which basically means anything, right? Because the max prefix length you can have is 32, the minimum being 20. So if it's less than or equal to 32, it's going to allow all prefixes based on this. So how is that different to the next statement? That is just 192.168.0.0/24. Well, this one's only going to allow that specific prefix. So if it receives 192.168.1.0/24, it's not going to be permitted on that second sequence, because it's not the exact statement. It has to be 192.168.0 as the network statement that it's receiving, right? On the top one, the difference is it will permit any advertisement that matches 172.20.0.0 because the first 16 bits match, but it will also permit 172.20.2.0 or 172.20.128.0, right? So as long as it matches this network's mask here, the 16, so as long as the first 16 bits, basically the first two octets, are exactly 172.20, then by saying less than or equal to 32, any other network statement beyond that is also accepted. Whereas if we had it like the bottom one, where it was just 172.20.0.0/16, and that's it, we didn't specify less than or equal to 32, it's going to look for permitting exactly that network. So if we received 172.20.0.0/24, it will deny it. But because we've specified less than 32 on the end, or 172.20.0.0/24 it does match, because it is less than or equal to 32 in length, so it's 24 in length, and the network statement here is 172.20 /16 is the same. So the first 16 bits match, right? So it's a bit complex, but if you wanted to be a little bit more complex on the specific prefixes and ranges that you want to permit or deny, prefix lists can be very handy, very helpful with being more complex in your definitions. But the trade-off with that is it can be a hell of a lot more confusing and a hell of a lot more easy to make mistakes. So just be careful. Make sure that you're interpreting these correctly when going into them, because it can quite easily lead you astray. And yeah, down the bottom, all I did was just show that prefix list so you can see what it looks like if you were to print it out. So yeah, specifically there's sequence 5 as the default. It's just good to be aware of that. Okay, so I know that was a lot to try and absorb. I highly recommend that you try and just implement these on your own and see how they work. But we will have some lab videos to cover off on some of these topics after this presentation. So lastly, what we want to move into here is the filter lists. Now this is it's different again, and this is where you're going to start to get really confused because there's so many similar things that you're starting to learn about that are slightly different. Now filter lists are used in OSPF and BGP, and right now all you just have to make sure you know is that they exist and that you're aware of them. Alright, so looking on the screen on the right, I've actually got both of them listed. Now the router OSPF 1 process is what we're going into in router 1, and you specify the area, so area 0. Filter list is the command that you use to use a filter list. And then I've used the question mark just to show the available options, and we can see the only option is to use a prefix. So if you're using a filter list, you have to specify a prefix list. That is the only option here. So on the next line, area 0, filter list, prefix, my prefix, in. And that's just going to behave basically the same way that you would expect with the distribution lists that we used in ERGRP before. These can be quite handy when you're controlling traffic when it's in a OSPF network with multiple areas, so an intra-area OSPF network. These can be quite handy to prevent loops and to control the traffic. Now, where else can you see filter lists? Well, just below in BGP. So don't worry too much about what's going on here. It's going to confuse you more than anything. You'll cover off on it in the actual BGP, advanced BGP lessons. But just a quick overview. We've specified an AS path access list. So IP AS path access list 99 permit, and then this regex, regular expression, on the end. And then we go to router BGP, the autonomous system number, into the IPv4 address family, and then we say neighbor, the neighbor address, filter list 99 out. So what's happening here is we're saying for this neighbor, we want to apply a filter list that matches the AS path access list of 99 out. So this is specifically an AS path access list, not an extended or standard access list. All right, this is different. It's an AS path access list, and then outwards towards that neighbor. All right, so just be aware of it for now, and you'll learn more about it in due course. Okay, and then the last topic for this video is thankfully something we've already covered off. We covered off on preventing loops with tags via route maps in the second route map lab video. So this is a screenshot from that lab video where we had a few different routing protocols with route redistribution. And basically what we did is on router 3 and 4, what you can run into is a routing loop because the OSPF external routes had a lower admin distance than the EIGRP routes. So once they were pushed into OSPF, to reach router 1, router 3 was going to router 4, and to reach router 1, router 4 is going to router 3. So if router 3 needed to go to router 1, it would go up, over, and down to router 4. Router 4 would get it and go, oh, I know the best way to get there. It's via router 3. And it goes up, over, router 3. Router 3 goes, oh yeah, I know where to send that. It's router 4. Up, over, down. And the cycle continues until TTL equals 0. Now what actually happened in our lab after configuring it and resetting the devices is one of them eventually actually figures it out and uses the correct path with the worst admin distance down because of the OSPF neighbor adjacencies and flapping routes, basically cracking a sad. So it did work in the end, so it got rid of the loop, but one of the devices was going all the way over to the other one to reach router 1, so we use route maps to change it. But what we do is, essentially, when it comes to the tagging, is as the routes are advertised into OSPF on router 3, we can tag it with, say, I don't know, tag 50. So for these external EIGRP routes going into OSPF, we say tag 50 on that traffic. And then on router 4, we set a filter using a route map and say, hey, check just in case, like anything that we're receiving, just check to see if it's got a tag of 50. If it doesn't, then that's okay, process it like normal. But if it does, if it's got a tag of 50, deny, drop that traffic. That way, router 4 is not going to look to router 3 to reach router 1, and it will use the proper path of going direct to router 2. Now we do the same thing on router 4 to router 3. We will tag the traffic going in using a different tag, say tag 99, and then on router 3 we look for that tag traffic of 99, and if it matches, if it has a tag of 99, then we drop it. Again, we went through all of this in a lab video already, so if you don't understand it, then make sure you go into that lab and follow through. Otherwise, that is how you can use tagging to prevent routing loops. Now, when you heard tagging, you may have instantly thought, hey, I've covered that before. I remember back to when I did CCNA, we had VLAN tagging, VLAN tags, right? That's not what it's referring to here, so don't get confused with that. That's at a layer 2 level, and is not what they're talking about here with the routing loops. Okay? So that covers off on the first two, being the filtering and the tagging. And then next we'll move into split horizon and route poisoning. Thanks for watching, and as always, please feel free to drop a like, subscribe, and if you have any questions, use the comments section down below. Otherwise, there's plenty of information in the description if you want to get in contact with us or support us any further. Thanks, and I'll see you in the next one.